Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we finished our discussion on the engineering classification of rocks and rock masses. So today we will start a new chapter on strength criteria for isotropic and anisotropic rocks. So before I go to the strength criteria, first we will discuss about the two materials, that is soil versus rocks. Then we will see that what do we understand by the stress strain relationship with respect to the rocks. Then we will learn about the plane strain loading. So to start with, let us first understand about the two materials. Both are the natural occurring materials, that is soils and rocks. So here we are going to compare these from the strength characteristic point of view. So the first head under which that I am going to compare these two is that how the material is being formed, like what is the characteristic of the material. Like soils, they are the classic particulate media. You know that these are three-phase system, and in case of the rocks it is disjointed continuum. You have seen that we have intact rocks as well as the joints in a rock mass. So basically these are modeled as disjointed continuum. There are significant scale effect in rocks, but it is not there in soils. I have explained it to you that when you increase or reduce the size of the specimen of the rock, how the strength is going to be influenced by that. In case of the soils, we do not have any of such phenomena. In case of the intact rocks which has no structural defects, it can be considered as homogeneous and isotropic, as has been shown in this figure. There are no discontinuities and therefore this can be considered as homogeneous and isotropic. But what happens in case of the rock mass? It is often heterogeneous and anisotropic. Why? Because of the presence of discontinuities. Take a look at these two pictures. There is one joint set and this I am calling as rock mass. Now in one case the loading is applied in the vertical direction and in another case the loading is applied in the horizontal condition. And if we have such type of joint set, like here it is this joint set, then in this case the stability is going to be better under this horizontal load as compared to the vertical load. Further, if there are more number of joint sets or if the rock mass is highly disjointed or it is the fractured rock, then it can be considered as isotropic material with large number of randomly oriented discontinuities, as has been shown in this figure. So you can see in this figure is that the discontinuities are oriented in such a random manner. There is no pattern. That means I cannot say that it has 2 joint sets or 3 joint sets or 10 joint sets. So we are calling this as heavily fractured rock mass. Soils are generally treated as homogeneous and isotropic, although they are not, but most of the theories when they were developed in the beginning, that is the first assumption which is involved, homogeneous and isotropic, be it shear strength theories or consolidation, etc. There are no scale effects in case of these soils, irrespective of the extent which is considered, the behavior of the soil specimen is going to be same. So, this is no scale effect. The second aspect where I can do it as soil versus rock is that in case of the intact rock, we get significant tensile strength, and in case of rock mass, little or no tensile strength is there because of the presence of the discontinuities. But what happens in case of these soils? Have you heard of tensile strength of the soil? Your answer should be no, because the tensile strength of the soil cannot be relied on, and therefore this does not make any sense. That is the tensile strength of soil. Good quality rocks with no discontinuities, it is possible to rely on some of its tensile strength, but not in case of the rock mass. But with good quality rocks with no discontinuity, we can rely on its tensile strength. Then the third aspect which makes the rocks different from the soils is that in case of the intact rock, you have very low porosity with no free water that is present, and this results into the low permeability. What happens in case of the rock mass? You have the discontinuities, and these can contain substantial free water, and as a result the permeability of the rock mass becomes very high. Presence of the discontinuities lead to the high pore water pressure, and therefore it reduces the effective stresses and the shear strength along the discontinuities. In the presence of the water, the shear strength of the soil also gets altered, but the way it gets altered, it is altogether different than that of the rock. Then the fourth criteria is the strength of the rock, intact rock, it increases with the confining pressure, and this increase is not linear, and it does not follow the Mohr-Coulomb failure criterion very well. See, in this chapter we will learn about the details of the Mohr-Coulomb criterion and other criterion which are more suitable for the rocks and rock masses. So, in the case of the rocks, failure stresses are better related by the Hook and Brown failure criterion, where the failure envelope is parabolic and not linear. But what happens in case of the soils? Most of the time we say that okay, Mohr-Coulomb failure criterion is fairly applicable in case of the soils. So, having these differences in between these two material in mind, let us have a look on the aspects related to in situ stresses and strength. Overburden stresses within a rock mass, they are computed in the same manner as it is done in case of the soils. Generally, the unit weight of rock is taken as 27 kilonewton per meter cube for computing the overburden stresses. Here in this picture, in situ measurements are shown corresponding to various depths from, let us say, very near to the ground surface up to about more than 2500 depth. And it can be seen that the normal stress, which is the vertical normal stress here on this axis, it varies linearly with the depth. That means the variation of vertical normal stress with the depth is the linear variation, which is given by this expression which is written here. So, sigma V in megapascal is given as 0.027 times Z, which is in meters. In normally consolidated and over consolidated soils, you all know that vertical normal stress sigma V is generally the major principal stress, and the horizontal stress sigma H is minor principal stress, and therefore sigma H is less than sigma V. In case of the normally consolidated and over consolidated, slightly over consolidated soils, the coefficient of earth pressure at rest, which is defined as the ratio of horizontal effective stress to the vertical effective stress, this is usually less than 1. But in case of the highly over consolidated soils, this ratio, that is this quantity, becomes greater than 1. What happens in case of the rocks? In case of the rocks, horizontal stresses are often larger than the vertical stresses. That is, generally your sigma V will be less than sigma H. In addition to in situ stresses within the rock mass, stresses are also induced by various tectonic activities, erosion and other geological factors, and these contribute towards sigma H being more than sigma V in case of rocks. In this case, as against the soil, K naught is greater than 1 and it can be as high as 3 at shallow depths, which are usually applicable in most of the civil engineering works. That is, most of the works are carried out at this depth only. So, within all the practical possible range of the depths, this K naught can take the value as high as 3. Because of this wide variability, horizontal stress should not be estimated in case of the rocks. So, in order to get the idea about the in situ stresses, let us take a look at this figure, where the data from various country with respect to K naught, which is sigma H upon sigma V, has been presented along with the depth. So, these countries from where the data has been taken is Australia, Canada, US, Norway or Sweden and South Africa, and there are other countries also. And then the two bounds have been drawn on this data. As you can see that this is the upper bound with respect to the larger values of K, and this is the lower bound on the values of K, and the equation of this lower bound is given by K naught equal to 0.3 plus 100 upon Z in meter, and the upper bound is given by 0.5 plus 1500 upon Z, which is there in meter. Then in 1994, Shorey incorporated horizontal deformation modulus in order to find this coefficient K naught in terms of EH and the depth Z, and this is given by this expression. So here this EH, which is the horizontal deformation modulus, this is substituted in gigapascal and the depth is written in meter. So this is how the coefficient, which is defined as the ratio of horizontal to vertical stress, can be determined. So I mentioned that because of the large variability, sigma h cannot be estimated. So what we do is we estimate sigma v, and then using this expression of K naught, which is sigma h upon sigma v, we evaluate the value of sigma h and then use it for the analysis purpose. Coming to now the stress strain relationship. You know that the stress strain relationship is also known as constitutive relationship or the constitutive model. Common constitutive models that you must have heard of, they include linear elastic, non-linear elastic, elastoplastic, rigid plastic, strain hardening, strain softening. Then in the elastic plastic mode, you have the Mohr Coulomb failure criterion, you have Drucker-Prager, then you can have viscoelastic stress strain relationship, viscoplastic, and the list is long. The question is how the strains are related to stresses, and the answer to this is given by this stress strain relationship or the constitutive relationship. So the simplest analysis of a rock mass can be carried out considering it as a linear isotropic elastic material which is following the Hooke's law. So how can we do that? So you see that I write the strain components. So the first one is epsilon x, which is equal to 1 upon E sigma x minus nu times sigma y plus sigma z. Then the next component is epsilon y, that is equal to 1 upon E, you have sigma y minus nu times sigma x plus sigma z. Then epsilon z is 1 upon E sigma z minus nu times sigma x plus sigma y. So these are the three components of the normal strain. Then you have the shear strains, which is gamma xy, that is equal to 1 upon g tau xy. You have gamma yz, which is equal to 1 upon g tau yz. Then gamma zx is equal to 1 upon g tau zx, where these sigmas, they give you the normal stresses, tau is the shear stress, epsilon is the normal strain, gamma is the shear strain. E and G, these are the elastic and shear moduli. is the Poisson's ratio, which varies between 0 to 0.5, and there is a relationship between G and E, which is given by G is equal to E upon 2 1 plus nu. So, you are aware of all these relationship. It is the basic elastic relationships when you have linear isotropic elastic material. Now, in the matrix form, how these stress strain relationship can be written, let us see. So, it is in the matrix form. So, I will have here as epsilon x, epsilon y, epsilon z, gamma xy, gamma yz and gamma zx. That is the strain vector that we have, and then this is going to be equal to 1 upon E, and then I will have this matrix 1 minus nu 0 0 0 minus nu 1 minus nu 0 0 0 minus nu 1 0 0 0, then 0 0 0 2 1 plus nu 0 0, then 0 0 0 0 here, again here 2 1 plus nu, and the last one is 0, and likewise we reach to the last row where the last element is 2 1 plus nu. So, this is your matrix, and then you have the stress vector, which is sigma x into sigma y into sigma z, then tau xy, tau yz and tau zx. So, this is how the strain can be written in terms of stresses. Similarly, you can write these stresses in the form of strains. Let us see how. So, here now we will have the stress vector, say that is sigma x, sigma y, sigma z, tau xy, tau yz and tau zx. That is the stress vector, and this is going to be equal to E upon 1 plus nu into 1 minus 2 nu, and then we will have the matrix, which is 1 minus nu, nu, 0 0 0, nu 1 minus nu, 0 0 0, then nu 1 minus nu 0 0 0, then 0 0 0, 1 minus 2 nu upon 2, 0 0, then 0 0 0 and 0. So, this is now 1 minus 2 nu upon 2, 0, then last row is 1 minus 2 nu upon 2. So, this is how this matrix is going to be, and then we will have on this side as the strain vector, which is epsilon x, epsilon y, epsilon z, then gamma xy, gamma yz and gamma zx. So, it is one and the same thing. The equations, they can be written in the matrix form. Stress can be represented in the form of strains, or the strains can be represented in the form of stresses. So, let us proceed further, that we have the volumetric strain, which is the ratio of volume change to the initial volume, and this can be written as epsilon volume is going to be equal to epsilon x plus epsilon y plus epsilon z, and then you have just substitute all those values of epsilon x, epsilon y and epsilon z as we derived in the earlier slides. So, this is going to be 1 minus 2 nu upon E into sigma x plus sigma y plus sigma z, or it can be written as epsilon volume is going to be 1 minus 2 nu upon E into, I can write it like this, sigma x plus sigma y plus sigma z upon 3 is the same expression, but this will be 1 upon k sigma x plus sigma y plus sigma z divided by 3. Okay, so here you will have this k as the bulk modulus. We already have defined E as the elastic modulus and G as the shear modulus. So, basically this k is defined as a bulk modulus and is given as E upon 3 1 minus 2 nu. Now, in some numerical modeling, some numerical modeling approaches or applications, these G and K, they are used as the input parameters rather than E and nu. So, therefore, it is important for us to know about all these. So, this E is going to be equal to 9 k into G divided by 3 k plus G, and Poisson's ratio, that is nu, is equal to 3 k minus 2 G divided by 2 times 3 k plus G. So, this is how that you can have the relationship between E, K, G and nu, that is the Poisson's ratio. Now, for these structures related to geotechnical engineering include retaining walls or embankments and the strip loading, they are long in one direction, and therefore, the deformation or the strain in the longer direction, it can be neglected. So, such type of deloading is called as plane strain loading. So, for a plane strain loading, these strains, they are limited to xy plane. So, let us write, in the light of this property, the stress strain relationship for plane strain loading. So, this is how that we can write it. So, we have first the strain vector, which is epsilon x, epsilon y and gamma xy. Because I mentioned that deformation or the strain in the longer direction, they can be neglected. So, I assume that the longer direction is z. So, you will not see any strain component in that z direction. This is going to be equal to 1 upon E 1 minus nu square minus nu into 1 plus nu 0, then minus nu 1 plus nu 1 minus nu square 0. then 0, 0, 2, 1 plus nu. And then you will have the stress vector which is sigma x, sigma y and tau x y. So, this can also be written as stress vector and this is the strain vector. Or like we did in earlier case, stresses also can be represented in the form of strains. So, we have here as sigma x, sigma y and then tau xy, that is equal to E upon 1 plus nu into 1 minus 2 nu, and then we will have this matrix as 1 minus nu, nu 0 and nu 1 minus nu 0, which is 0, 0, 1 minus 2 nu upon 2. And then here we will have the strain vector, that is epsilon x, epsilon y and gamma x y. So, this is how we have stress vector here and this is the strain vector. Now, what will happen to the normal stress which is perpendicular to the plane? So, you see that the plane strain loading, it does not mean that there are no normal stresses in the direction perpendicular to that plane. So, normal strains 0 in that direction which is perpendicular to the plane, and in this case we have taken that x y plane, and so perpendicular to that plane is the z axis. So, normal strains are going to be 0 in that direction, but not the normal stresses. So, what is going to be the normal stress in the direction which is perpendicular to the plane? That will be given as sigma z, that is equal to nu times sigma x plus sigma y. And how you can determine this? You know that epsilon z is equal to 0 when you have the plane strain loading. So, I have given you the expression for epsilon z, just substitute that to be equal to 0 and you will get this expression, that is sigma z equal to nu times sigma x plus sigma y. And therefore, in case of the plane strain loading, you will have the non-zero stresses as sigma x, sigma y, sigma z and tau x y. And you will have the non-zero strains as epsilon x, epsilon y and gamma x y. So, this is how the stress strain relationship or the constitutive relationship for the plane strain loading can be obtained, or you can use these in the analysis of the structures which are going to be there in the rock or rock masses. So, this is what that I wanted to discuss with you. So, just to summarize, we had the discussion about the soil versus rock. Then we discussed about these constitutive relationship, that there can be different types of the constitutive relationship. And to start with, we discussed about the linear elastic theory, and I mentioned to you about the stress strain relationship, and then I explained you the concept of plane strain loading. In this context, I suggest you to remember that the normal strains, they are 0 in the direction perpendicular to the plane where we are considering the structure, but not the normal stresses. So, in the next class we will discuss about the plane stress loading, axisymmetric loading, and then we will continue with different failure criterion which can be applicable in case of the rocks and rock masses. Thank you very much.